is one of the common mistakes. The other common mistake, I see students cannot find family chain. So it should be the longest one. Well, I didn't really read. I think either this one or this one works. They should. That's the same, right? Okay. Any question on this one? Yeah.
For the first question, for the one on the left, isn't it 1-methyl-propyl?
Yeah. 1-methyl.
No.
Yeah.
Oh, I'm going to shame on the.
And also, for the first one, can you say 1s, 3s?
Yeah, sure. Yeah, if you did that, I will still give you full credit. Yeah. If you identify the R and S, it's the same do trans or cis. But I would say do trans is easier than say R or S. So yeah. Okay. Number 3, this is a stronger base because on this compound you have 2 electron withdrawing group, but this one you only have 1. That's the EWG. Whenever you have electron withdrawing group, you are going to steal the electron from your neighbors, and your neighbors are not going to be happy to donate more electrons out to behave like a base. Usually this question is asked in a way that which one is more acidic. So if I put a hydrogen here and put a hydrogen here, so this hydrogen is really acidic. Also hands out the priority table. On the back of that is the pKa. If you check, this one is actually on that. It's really acidic. I hope you all get the resonance structure. So this time we're just using the long pair, change to here, and then forming a carbon-carbon pi bond. That's basically what it is. Enantiomers and diastereomers. It's something based on you have no order R or S O-phase compounds, and then you start to think about what's the relationship between 2 compounds, which they have everything the same apart from chiral center. So they're basically the same thing, but the only difference is chiral center. So if I'm going to use models, enantiomers means you have this one, zoom out maybe. Okay, you have this one, which looks like this. And then if I change the blue and the orange, it's going to be its enantiomer because I definitely change the RS of this carbon, right? So how do I know that? The relationship between these 2. So that's the relationship we're talking about when we're enantiomers and diastereomers. So that's the rule I use. Only if all the stereocenter in the molecular are opposites, they're enantiomer, which in this case not, because I only change 1 carbon. Otherwise, diastereomers, which is this case. This is something that's after you identify all the R and S. On worksheet 5, I just have you identify all the stereochemistry in this compound, and then you start to compare. I identified that already for you, so I just want to make the things clear. It's RRR and RSS. So our rule is only if all the stereocenter in the molecule are opposites, they are enantiomers. So in this case, they are diastereomers because 2 of them, one of the stereocenter is the same, they are R, and the rest of them are opposite to each other. Did I make this point clear? So that's what I mean by. So on your discussion menu, he only used a compound with 2 chiral center, and it's really confusing because how do I know what else? So my rule is only if all of them are opposites. Otherwise, diastereomers. And what if all of them are the same? If all of them are the same, they are identical. So there are only going to be 3 conditions in this case. All of the chiral centers same, identical. All of them opposites, enantiomers, whatever it be between these 2 diastereomers. Did I make this one clear? Okay, so that's basically what I can say on diastereomers and enantiomers. So it's something after you practice on identify R and S. That's the only part I didn't finish. But we can still go through your discussion menu, and to see what they say about. So that's still note 4, which is enantiomers and diastereomers. So I don't really use the book, but that's I think it's this page. So you don't need to know those. Oh, you do need to know how to draw the feature projection. So this one, I would say you just you need a model to look through that. So this one is basically still the same. When you have that cross, you are just looking like this. So that's the cross you see on the paper. So 2 of them, actually they put those 2 wedged up. Okay. So these 2 are the wedged up, and these 2 are the dashed in. So that's basically still a chiral center. The best way to do this one is to build a model and to really rotate that into the conformer that's on your discussion menu, which I think you probably just need to practice on 1 or 2, and don't spend too much time on it. So that's what I can say. Just the way that it works is from this to this. So you need to practice on how to look at the molecular and rotate in your head and make it into here and sketch out what you see. So in this case, what is previously wedge is actually one of them is dash, one of them is wedge, and then you put this bond into the plane. So that's something, as long as you practice on 1 or 2, you will get it. Okay? So that's for on your discussion menu for this. It's not really okay. So that's what I'm referring to. I don't like this page because I don't think it's clear. But as I see here, S, S, R, R, they are all opposite to each other, so they're enantiomers. But if they're one of them the same, like S, S here, A, S center in A and S center in D, they're diastereomers. The same for the rest. But my rule works for all the compounds. This one, when I was a student, I don't like this page because it tells me nothing. Agree. Okay. So you all know how to differentiate enantiomers and diastereomers now? Good? Okay. See, there's another sample, but it still don't only have 2 chiral centers. So what happens if I have 3? That's really nothing. Oh, assigning R and S. There are stepwise steps in your discussion menu, which I think it's too much things to read. I will just follow the 1, 2, 3 step in my notes to assigning them. That's it. Practice on those stuff. Do you want me to do an example here or not? Oh, okay. So let's just practice on compound E. So that one looks a little bit difficult. Compound E. Practice on identify R or S. So it's not that hard, right? So on your discussion menu, it asks you to assign in the priority, which is also my first step. Do you have questions on assigning priority why hydroxyl group is number 1? So do you have questions on that? No? So assuming you all know that's number 1. And then when comparing okay, I will say one thing more about why this one is number 2. Because for this carbon is bonded to 2 carbon. So both bonds are bonded to carbon. But this one is only bonded to 2 carbon. This one is 1, 2, 3. So this one with. So the side 2 with. So it's always, after you comparing your neighbor, then move on next. Number 3 and number 4. So in this case, the discussion menu asks you to flip over to draw this out. But what I usually do is if my lowest priority group is not at the dash position, I will still assigning R and S, but just I flip my answer. Does that make sense? So I don't really need to draw out this one. I know my 4 is in front, so 1, 2, 3, it looks S. It's counterclockwise, it looks S, but it's R. Does that make sense? So in my answer key, I do that a lot. So make it clear here. So this is number 1, number 2, number 3, and my hydrogen is pointing out. So it's counterclockwise, it's S. It looks S, but it's R because my number 4, lowest priority group is in the front, which should not be the case. I should put the lowest priority group at the back of the paper. So I won't redraw the whole thing. What I do is I just flip my answer. Does that make sense? A common mistake in this part is a question. I probably mentioned that last week or no, I don't remember. So it's you have 4 bonds, but one of them have a really like a higher priority group far away. But this one has a carbon double bond. This one is OH. This one is hydrogen. If this is the case, although bromo have higher priority than the rest of those, this one is too far away. You cannot compare directly. You cannot put this one as number 1. You should always start your first neighbor. So this first neighbor is carbon, oxygen, hydrogen. This one went already. Did I make this point clear? So don't think, oh, there's a bromo, then this is number 1. No. Because your neighbor's neighbor, you probably don't really know who he is. This is the neighbor's neighbor. This one can have very little effect on this carbon. So don't do that. That's a common mistake I see. If I were the one who's making a quiz for RNS, I will design this kind of question. So it's kind of, I'll let you know before. And then which one is the next? Should be this one, because we just talked about this before, right? This carbon is bonded to carbon number 1, number 2, and the rest of them are hydrogen. This carbon is bonded to carbon 1, 2, 3, because both bonds are bonded to carbon, so this one wins. This is the number 2 priority, this is number 3, this is number 4. So that's the trick in assigning priority. If it happens in the ring, it still goes to that. Another common mistake is this might not be a chiral center, because what happens in the ring, you really need to compare. Sometimes, I think maybe I called that before. For this carbon, this is really not a chiral center. This is not, because although it looks like, oh, it has something else, but these 2 sides are basically the same. So this carbon is achiral. You cannot assign R or S on this one. Did I make this one clear? So that's two common mistakes. One is didn't compare neighbor by neighbor. One is didn't realize that this one is not chiral center. So note 5, IR. This week IR, next week and the 3 weeks after NMR. Those are spectrums, which is what I will describe like a chemist, the eyes of chemist. We know nothing about chemistry unless the machine told us what compound it is. And those are the stuff that's the language of the machine. So if you turn the page to 93, this is what kind of question that you're going to meet in your final. I don't think it's going to be like that hard in midterm 2. So this is like they gave you the formula, the compound A here, CaH17BrO, and then they gave you 2 spectra. You are supposed to write down what the structure of the molecule is. It's kind of solving for puzzle. It's fun, but you need to know the language first. This week we learned spectrum this. So IR is the one has the x-axis really huge number. From next week on, we're going to learn NMR, which is the one with smaller number. So it's just interpretation of spectrum. And then the note 5 I hand out is actually also coming from this menu. Is this page. So on my note 5, this table is actually the same thing here. But I would think carrying the whole stuff is kind of, I won't do that. I will just look into the table. I will teach you guys how to use the table, so it makes sense. It's part, which is for carbon, I don't really think you're going to learn it in 118A. But this is the whole tools that I'm going to use, even as a researcher. So not for study organic chemistry, I still use this page for a lot of things, just like solving my own puzzles in Spectrum. So it's kind of a handy, although you might not need to use it right now. Okay, we are responsible for IR this week. So what's the IR looks on your discussion menu? It's not the real one. It's the ones that they want you to identify, which is kind of talk to the spectrum. So you can see very clearly, they have a peak like this. That's what they're trying to tell you. If you have something like this, it means it has a functional group. I can tell you now, it's OH. And the same for this. It told you there's a sharp peak. That's really a sharp peak. And in the region of like a lower than 1500, those parts we don't really look into it because we call this region fingerprint region. Everyone has finger, and a fingerprint is different from others. So this area is kind of messy, and we don't really want to look into it. It's different for each single molecule. So that's the region we don't look. We only look here. So after 1500 to the end. Now what I'm going to show you is the real spectrum. So it's something that's, after you see the real one, you will know the discussion menu is kind of nice, it's really immersive, it's really nice to you guys. Okay, this is the real one. I will upload it in my email because it's too much to print out, so I didn't really print out for you guys. This is the real one. So in reality, you do really need to see, compare with the peak on your discussion menu. There is a broad one right here. So that's what it looks in reality. Then the discussion menu telling you there is a peak here. The best way that I think to learn this part is to read enough spectrum, which what I'm going to do now. So I have a lot. And we're just going to see if this table is going to work and how this table works. So this is kind of a practice. I have 5 molecules here, and then I'm going to match them with that, and I have the answer next to it, and I'm going to make sense with it. The first thing I want to teach you guys is the hydroxyl group, which is the huge one. It's usually really obvious. And on the table, it's also the same in your discussion menu. OH is here, alcohol. So it's about 3,000 to the end. Same thing for amines. So see, they are really close. And then you can, I would say I won't really differentiate these two, but usually hydroxyl groups has a stronger bond. This one is not that strong. So let's see how that's going to look here. So remember, this compound has hydroxyl group, and it's almost touching the base of the spectrum. So that's what we say strong. It's a really deep overbond. Make sense? Okay. And then what else do this one have? It's all saturated carbon hydrogen. So on the table it says alkynes. It's in this region. It's about 3,000. This is a region that I don't really look because, which is here. That's respond for the bond for alkyne, which is carbon-carbon or carbon-hydrogen, all kinds. See alkene, which is double bond. This one, the hydrogen associated to double bond, is also in this region. It's just a little bit higher than this one, which is, this one doesn't have, but we will see, maybe find one. Okay, see this one. This one, also hydroxyl group, a deep overtone, and then this one has sp3 and sp2, which is the alkene. We say it's going to be about 3,000 and a little bit higher. So this is the sp2. I will erase this one. This is the sp2. So you just I will think this one is is really hard to tell. If you just give me a spectrum, it's not really good evidence to look at here. So carbon-carbon double bond, which is this one, also have another peak on the table. This is really obvious, 2000. So about 2000 is usually in the region of this. So see 2000, 2100 to 22. 21 to 22. Oh, okay. So this one is actually not this one. I'll talk about this one. This is also carbon-carbon, but it's carbonyl. It's the resonance structure of this one. So it's here. So carbon-carbon bond. I think this one is also. Maybe they both are, but that's how you look. It's not that obvious, but when you see a small peak like here, in the region of about 2000 in the table, that corresponds to double bond. And how do I know this one is carbonyl? Because carbonyl usually is here, is around 1700, I believe. Yeah, carbonyl, see? It's around 1700. So that's kind of, I don't really remember exact number. I just remember, oh, this region is carbonyl. But usually, carbon double bond is in this region. This is the region responsible for that. The one more obvious is the carbonyl here. See, that's a huge carbonyl. So carbonyl group usually have a deep overtone. That's just what it looks like. One thing more, why this one has a carbonyl, because this one can have a resonance structure like this. This one. See, resonance structure everywhere in organic chemistry. I solved those questions myself because this one doesn't have the answer key when I search online. When I was doing this question, both compounds have hydroxyl group, so I know it's either going to be this one or this one. And then this one has double bond, and this one too. So this is definitely going to be the spectrum of this one. But this one, you don't see clear double bond. So I know this two. And I know this one because they're a deep carbonyl, and it's a real one. So I know this two. Then the only thing left is this and this. This is epoxide, and this is also a ring with oxygen on it. I know it's going to be these two, but how did I differentiate these two? It is by this. So it also has something to do with this. I think when I was doing this question, what exactly in my mind is this one is really hard to form carbonyl group because of the angle strength. This is already kind of really active to react with a lot of things because you really want to open a ring, but this one is better. So it's more likely for this one to have a carbonyl group and a little bit OH. If it has a resonance structure, that hydrogen, that oxygen needs to have a hydrogen on it. So I think this is this one. And because this process doesn't have the answer key, I really search there is a Japanese website called SDBS. I can send the link in my weekly email. There is the compound it's like the database for all the compounds. They have all the IR, all the NMR for whatever molecule you want. You can just type in. So after you enter into that link, you type C4H8O, and it's going to give you the whole list of all the compounds with the same structure. And then you can look into each of them to see what's the spectrum like. It's kind of, if you are doing your own research and you sense something you don't really know, and then you start to guess, maybe this spectrum is this, and then you search in that website to see if that's the real case. All the data are real, not computational, so it's really handy. I look into that, and I think this is exactly the spectrum of this one. So that's exactly how I solved this problem. I told you guys. Then what you guys need to do is we go through the rest of the example, which is they have the answer key just next to it. After you see enough examples, you will have a general idea where which functional group should be. And let's just go through this exercise together. So this one has hydroxyl group. So this is this. We've seen this before. And then this one doesn't have any carbon-carbon double bond. So see, this region is really pure. And then it doesn't have that sharp peak here. So this is basically what it is. This one, so I'm going to hide a little bit. So you can have a guess. Okay, have a guess of this one. First, it doesn't have, what this told me, it doesn't have hydroxyl group. And this one is around 117. It definitely have a real carbonyl. And this one, we say this is still the region of double bond. This might be a carbon-carbon double bond. One of them is going to be. So I don't need you to tell me which one is which, but you should be able to tell me there are double bond and carbonyl, no hydroxyl. Makes sense. And let's see, this one also telling me there is a hydrogen bonded to carbon-carbon. That's the sharp peak we talked about at 3100, right? So what this compound look, it do have a hydrogen here. And then it has carbonyl and a double bond. It doesn't have hydroxyl. This one is a one that's really complicated. I will show you the structure first. So this one has triple bond, but it's not really shown here. Probably we should save this one for later. I will show you a triple bond first. This is the triple bond, normal triple bond. Normal triple bond, which is here, the cyanyl group. I'll zoom out this bit. The cyanyl group is the triple bond. So remember, this region is double bond. The region next to it is triple bond. So that peak, really sharp peak, is responsible for carbon triple bond or carbon cyanyl. So look into the table, it's still within the region. And then it doesn't have any saturated, so like this one before. It doesn't have any those, which means all of the hydrogen carbon in this bond are in somehow sp2 or sp3, which is the case. So you can see nothing in this region. Usually you will see if it's CH3. Make sense? Okay. And then what if this group corresponds to this peak? This is carboxylic acid. So you do have hydroxyl group, which usually looks like this. But since you have a carbonyl next to it, it's shifted the peak a little bit. So just remember that. And also the strong carbonyl group here. It's just the case. You need to remember. This one, I might see NH2, that's also in the same region if it's on the table, but it's not as huge as hydroxyl group, so this is the NH2. And carbonyl. And your sharp sp2 bond, you cannot really see here because, oh, you still have it. Okay. Sometimes it's merged into the other functional group is fine. So here you can still see the peak. That's it. Did we see this one before? Okay, hydroxyl group here. Carbon-carbon double bond, that's the sharp peak. Otherwise, no. So this one is also the resonance structure, the fake carbonyl group. This one, that's the normal saturated carbon and a carbonyl. This one. So that's how I look. You don't really need to look into it. See, the only thing I do is within this region. This one, NH2 doesn't really show up because it's a symmetric compound. That has something to do with the introduction part, which I basically skipped. IR always has something to do with stretching the bond. But if your molecular is kind of symmetric, then you cancel out. The machine cannot see it. So just remember that if some of the peak is going to disappear if your molecule is symmetric. But we are not going to ask you that kind of hard question. Make sense? And then after we see this one, we'll come back to the one that I skipped. So this is still the triple bond. That's a small peak. And because this molecule is still kind of symmetry, because if I made a molecule of this one, so this is just 3 methyl group, and this cyano group, we know SP is 108 degrees, so it's basically pointing up. So this is the one, looks like this, because cyano group is 180 degrees, so the molecule will look like this. It's still kind of symmetrical, like all of those are methyl groups, so you have actually 3 mirror plane for this molecule. So it's still kind of symmetric. So this triple bond is not that obvious as the one that you've seen before. Make sense? So symmetric molecule is going to be a little bit different. So the one that I escaped is this one. See? This one has a triple bond, but triple bond disappeared because it's totally symmetric. Does that make sense? Okay. Now if we back to your discussion menu, after you see the real one, your discussion menu is basically trying to teach you, I have a bond here, you need to tell me what this is. So what's that one? OH? Okay, it's hydroxyl group, certain names, okay? So that's kind of the same exercise that I was doing. You can practice on your discussion menu with those compounds. Have a play with it. What we do for IR, in reality, when I was doing research, I made a sample and put them into the machine, which is was IR, the machine for IR, so that's FTIR. I put the sample in, and the machine is going to shoot a IR light into the sample. From the light of whatever, I think I usually use from 400 to 4,000. So they shoot a light after every 3 seconds or 2 seconds. That's from 400 to 402 to 404 to 406 until 4,000. And each of them is going to give me a spot. When I collect all the spots together, it's going to give me the whole spectrum like this. So those are the like a spot, and you collect the spectrum. So what Fourier transfer do, the FTIR, the FT mean, it means you do them at the same time. So you shoot the light at the same time. It's kind of playing the piano. So what I did, what I described previously is you press the key one by one. And what Fourier transfer do is you push the whole bunch of keys at the same time, and the machine is going to calculate each one of them for you. So it's just save you some time. Did I make this one clear? So you do this on your piano, and all of them is going to make huge noise, but they collect the noise, and they can calculate for each one where your spot is. That's what Fourier transfer do. If you are interested in that, you can watch a video online. I watched that, and it still doesn't make sense to me. So that's I use piano to explain it. It's all mathematics. You just need to know it's the same thing as press one key at a time and collect all the points. Okay? Okay, so for the one who take this version, there's a multiple choice because none of the 4 answers are correct. The F question, I'll zoom out of the. So if you're doing this question, I think it's either pink or white has this question. So if you get something, if you are choosing either C or D, you get 1 point. If you just write here, say no, it's not correct, you get the full 2 points. I know it's unfair, but it's the same for everyone. Because one of the TA who found that mistake during the midterm, and then he cannot shout out, say, we need to change one question. Then everyone knows that is the correct answer. So the only thing we can do is just let it go. And this one is only 1 point. And then because Neo usually curve by the type of exam, So it's the same. If you are taking this one, that's don't think that 1 point is unfair to you because you are still curved. So you are comparing with the people who do the same paper result. Did I make this one clear? I think you guys are doing well under this, but in order to make you guys do better, I hand out the worksheets 5 to 8, and then the midterm, the practice midterm for the second one, right? So let's talk about this thick stuff. I want you guys to bring the stuff with to the class from now on. So next week, I'm expecting you to take the whole thing. The reason I give you guys off is because I want you to see what a real chemistry exam is. It's going to be something like this. Not describe what is this and well, you still have mechanisms, and this time we are really we didn't really get all the points off for your arrows, even you draw the double one. But next time, your midterm 2, practice midterm 2, I gave you out one, so you still have a lot of multiple choice. You have nomenclature and conformers. This is a new type of questions that you don't have before, which is writing out the products of a reactions. And then you need to know that's the real chemistry exam looks like. It's going to be like this forever. So as one day you are still in chemistry, you are going to meet this question. I guarantee you. And then you're also going to do a mechanism one. So let me see if there is one. So include the mechanism. So that's the words I write on this board. On the first discussion, mechanisms, which is the one that we made on the flashcard last week, we are going to make for next week. So although you probably is going to learn one, but I'm going to teach you the rest. And then you can get a start to do the things you want. And then by the time you really learn it, so chapter 6 and 7, they're basically the same thing. He's going to cover that in next week. Probably he started already yesterday. Did he start it? Chapter 6? No? Okay, so by the time we meet next week, you probably have already learned the majority of chapter 6. And I'm expecting you to jump on to chapter 7. That's what's going to be covered. And see the IR question. Do you think it's that hard? I would say if you practice with me, it's not that hard. So this one is a hydroxyl group. So I'm going to choose the one between this and this. And then this one doesn't. This one has aldehyde, but this one doesn't. Maybe. Oh, this is small. It's not a real aldehyde. So it's going to be this one for me. So that's kind of the question that you're going to meet. And this table. So remember in the first discussion we talked about a table, 1 page and a half reaction, and then a map. This is the first thing, the table. I attach it here, and if you actually see worksheet 7, there is use the table, use table. See? So that's why I put the table at the back of the worksheet. So start to be familiar with the question on this, and then get ready for the next midterm. Okay? Okay, that's. Oh, I'm going to return the quiz, but contents, that's it.
How do you like my hand?
One hand.
No, it's
The other one is like
because you
three,
hit that
five,
subsection first.
And you go 5, 6.
Yeah.
So you're dealing with
It's always
4, 6, and 3, 5.
I see what you mean. Okay. So maybe the TA didn't mess up. Never mind. Okay. Because we have passed the time for dropping the class, I will start to learn you guys' name. Because I know before that, I usually just ask you guys to come to me, because I know some of you is going to leave me for whatever reason. But now we passed the class time, right? So only if something really serious happened to you, we are going to spend the rest of the quarter together. Okay, so I think it's alphabetical order, but I will try to pronounce your name, you guys' name, as much as I can, but I'm also a foreigner, okay? So be tolerant to me. Clara. I'm going to stop the video. Don't. This, I'm not going to look bad on this one.